Hello, this is Lab 5, Magnetic Braking with Faraday by John Cutrone. The main goals of this lab are to obtain the experimental data for a bar magnet falling through a conductive tube of aluminum foil, create a simplified computational model of the same experiment, and compare and contrast the experimental and computational results. The findings of this lab were that the experimental average time through the tube was 1.154 seconds, and the computational time through the tube was 0.966 seconds. The major physics concepts involved are Faraday's law, which is used to find EMF, Biot-Savart's law, which is used to find the magnetic field from a dipole, Newton's second law to find the net force, the magnetic flux time derivative specific to this lab, Ohm's law, which is used to find current, and the magnetic force on a loop as shown below. The procedure was to first determine the north pole of the bar magnet using the magnetometer app from Lab 3. Then, while recording with the camera, the bar magnet was dropped through the tube 5 different times, and using the replays of the videos, the times were found. The systems and surroundings are shown. The system is the gray aluminum tube and the bar magnet, and the surroundings are just the room surrounding the tube magnet system. The red arrow represents gravitational force, and the purple arrow represents magnetic force. Some assumptions that were made are that the bar magnet falls in a perfectly straight line towards the ground, air resistance from the bar magnet falling is negligible, and that no other force besides the magnetic and gravitational force is acting on the bar magnet. The observations from the experiment are shown with the length of the tube, the inner width of the tube, the width of the aluminum, the magnetic dipole moment from Lab 3, and the mass of the magnet. And after 5 trials, the average time that was found was 1.154 seconds. The glow script code below shows the initialization with the graph and the constants, as well as the different values talked about before, and creating the tube of aluminum foil and code. Then the glow script functions for the dipole of B, as well as the flux analytic are shown. And finally, the simulation loop and the plotting on the graph are shown here. And this created this graph and this model. The model did have red and blue colors as the simulated magnet fell, but this is the end, and the graph shows the velocity versus time graph. The comparison between computational and real-life models, as talked about before, the experimental value was 1.154 seconds and the computational time was 0.966. Both times are very similar, however they do differ by 0.188 seconds, and the error between the two models can be explained by possible sources of error discussed in the next slide, which are that the magnet might not have exactly fallen straight down, causing slight altercations in the induced current magnetic force, human error when timing exactly when the magnet enters and leaves the tube, and miscalculated observations of various lengths and strength of the magnetic dipole moment. The intensity of the coloring on the tube indicates the magnetic of current flowing through each ring. Red and blue indicate the current flowing in opposite directions. Which color corresponds to different directions, and how do I know? The red current is counterclockwise and the blue current is clockwise, and this can be determined with Lenz's law. What happens to the dynamics of the system when you flip the magnet around? Nothing different would happen, however, the current in the aluminum tube would be flipped as the magnet falls. And how does the total time in cube of your real-world system compare to that of your computational system? As I said before, they're very similar but not exactly the same. In the computational system can be made more accurate to account for small air resistance and altering trajectories of the magnet. In the velocity versus time plot, what does it tell you about the forces? Well, the velocity decreased at an exponential rate at the very beginning, but then it stabilized, and that's why that there was a flat. In addition, If the resistor was reduced to near zero, then the induced current would be much greater and would make the magnetic force greater and possibly keep the magnet floating in the air or fall much slower. And if there were holes and slots in the aluminum foil, the disruption in the small simulated loops would cause the magnetic force to reduce, thus causing the magnet to fall quicker than before. Thank you.